Hi guys! In this video we're going to be looking at ratio of wave speeds in different media, Snell's law, and we're going to finish with a summary. So we're going to start off by looking at the ratio of wave speeds in different media. So far we've established that when light moves through different media, its speed can change because different media have different optical densities or refractive indices. So now we're going to look at the ratio of wave speeds in different media. The angles of incidence and refraction are measured as the angle between the ray and the normal either side of a surface interface. So this line here is our normal because this is our interface between two different media. So the normal is perpendicular to the interface. And this is our light ray entering this new medium. So we say that this is the light ray that's incident. And therefore we call this θ1, and θ1 is the angle of incidence. Then we can see when this light ray passes into the new medium, its direction changes because this new medium has a different refractive index and a different optical density. So we call this new angle with the normal, which is θ2, we call θ2 the angle of refraction. Because we say that when light enters a new medium and changes speed and therefore direction, it's been refracted. Consider two rays of light hitting an interface. Each ray must be perpendicular to each wavefront. So these are rays, and the purple lines are our wavefronts, and we can see that the rays are perpendicular to the wavefronts. And the blue line here is again our interface. Successive wavefronts mark the same phase at constant intervals of time, the time that passes with the distance of one wavelength. So the distance between wavefronts is the wavelength. So therefore we have a constant time interval between each wavefront, which we call delta t. And in fact, delta t is also known as the period of the wave, because it's the time taken to complete one full cycle, so for the wave to move through one complete wavelength. And we've also got delta t between these two wavefronts here in the new medium. We only need to consider the rays passing through the interface, the last incident wavefront, and the first refracted wavefront. So what we mean by this is we're going to consider this triangle here and this triangle here. So we've got our rays passing through the interface, we've got our incident wavefront and our refracted wavefront all here. And we're going to label each corner of this quadrilateral. So this is P, this is R, this is Q, and this is S. So that means we're going to call this side here PS and this side here RQ. The angles of incidence and refraction can be labelled within our boundary. So we've said that this angle here, θ1, is the angle of incidence, and then this angle here, θ2, is the angle of refraction, because they're the angles that the incident ray and the refracted ray make with the normal. And using angle rules, we can actually work out that this angle here is θ1 and this angle here is θ2. And we also know that this side we've labelled RQ and we've labelled this side PS. And the reason why this angle here is θ1 and this angle here is θ2 is because we've said that the rays are perpendicular to the wavefront. So this angle here is 90 degrees, which means this angle is 90 minus θ1. So therefore, this again is perpendicular because we said that is the normal to the interface. So that allows us to actually conclude that this angle here is θ1, because if this is 90 degrees and this angle is going to be 90 degrees minus 90 minus θ1, so we're saying that that angle is 90 minus θ1, we can see that it's actually 90 minus 90 plus θ1. So that's how we get that this angle is theta 1, and the same applies to this other angle, which is theta 2. We can extract the similar triangles from within our boundary to compare their properties. So we've said theta 1 here, theta 2 here. This side we've labelled RQ, this side we've labelled PS. And we said that this point here was P, this point here was R, Q, and S. So that tells us that along the interface, this length is PQ. So this will be easier to label on the extracted triangles. So the first one here has angle theta 1, and this is the angle made with the incident wavefront. So that's what we've got here, the incident wavefront. So what we've extracted is this triangle. So that means that this side here is RQ and this blue line is PQ. It's the side of the triangle that's along the interface. So we're calling this PQ. And now we can also label the triangle that is made up of the refracted wavefront. So we can see that the height of this triangle is PS, and this side is also PQ. Also, both of these triangles are right-angled triangles, and we also said that this angle here is theta 2. So these two triangles are similar because we can see that they've got the same side here, they share the same side, and they're also both right-angled triangles. We can use trigonometry to find equations to relate the angles and distances from each triangle. So we've got RQ, PS, PQ and PQ, and then we've got theta 1 and theta 2, and these are also right angles. So we can write that sine theta 1 is going to be equal to RQ divided by PQ, and sine theta 2 is going to be equal to PS divided by PQ. So sine theta is opposite divided by hypotenuse, so that's what we've done here. The distance between the rays along the interface appears in both equations and can therefore be used to equate them. So we've got that PQ is equal to RQ divided by sine theta 1. So we get that by rearranging this equation here. So if we multiply both sides by PQ and divide by sine theta 1, this is the expression we get. And we can do the same for the other expression we have. So we get that PQ is equal to PS divided by sine theta 2. And we can then equate them. So if we equate them, we've got RQ divided by sine theta 1 is equal to PS divided by sine theta 2. The distances RQ and PS are the distances travelled by the incident and refractive ray in the same time interval. So we've said that this here is RQ and this here is PS. And this is the distance travelled in a time interval delta t. Now, even though the wave speed has changed and its wavelength has changed by passing into the new medium, its period has stayed the same, because remember, delta t is also the time period of this wave. So delta t is the same in both media. And this is because the frequency of the wave doesn't change when it moves into a new medium. And we know that time period is 1 divided by frequency. So if the frequency doesn't change, then the time period doesn't change. So therefore, this time interval delta t does not change either. We can use the wave speed equation to find the speed of the incident and refracted rays. So we know that from the wave speed equation that wave speed is equal to distance travelled divided by time. And we can rearrange this equation for distance. So distance is equal to speed times time. So that means we can rewrite our distances RQ and PS in terms of that time interval delta t and the wave speed in each of the media. So in the first medium, we can say that the distance RQ is equal to the wave speed in medium 1, which is C1, multiplied by the time difference, delta t. And then we can do the same for the distance PS. PS is going to equal to C2, so the wave speed in the second medium multiplied by delta t, the time interval between two wavefronts. Since the time interval is constant, we can equate the two equations to find a ratio between the speeds in each medium. So we can rearrange each equation to make delta t the subject. So we've got delta t is equal to RQ divided by C1, and we also have delta t is equal to PS divided by C2. And we can equate these two equations. So we end up with RQ over C1 is equal to PS divided by C2. And we can then rearrange this to get a ratio of C1 over C2. So if we divide by PS and multiply by C1, we end up with RQ divided by PS is equal to C1 divided by C2. We can substitute the equation for the distances RQ and PS in terms of the angles of incidence and refraction into the ratio of speeds. So we found previously that RQ divided by sine theta 1, where theta 1 is the angle of incidence, is equal to PS divided by sine theta 2. And theta 2 in this case is the angle of refraction. And we can rearrange this to get RQ over PS as a ratio of sine theta 1 and sine theta 2. So we end up with RQ divided by PS is equal to sine theta 1 over sine theta 2. And we also know that RQ over PS, we've just seen here, is equal to C1 over C2. So that means we can also equate sine theta 1 over sine theta 2 to C1 divided by C2. The ratio between the speed of light in two different media can be given in terms of the angles of incidence and refraction. So we can say that sine theta 1 divided by sine theta 2 is equal to C1 divided by C2. And in this equation, we're saying that theta 1 is the angle of incidence, theta 2 is the angle of refraction, C1 is the speed of light in the first medium, and C2 is the speed of light in the second medium. So now that we've found a ratio of wave speeds in terms of the angle of incidence and the angle of refraction, we can actually take this a step further and find an equation that also involves the refractive index. And this formula is called Snell's law. So now we're going to see how we can derive this. The refractive index of a material is the ratio between the speed of light in a vacuum and the speed of light in the material. So, for example, here we have a vacuum and we have another material. And we've got a light ray going from the vacuum into this new material. And we can see that the distance between the wavefront has changed. So the wavelength has changed and therefore the speed of light has changed as it's travelled into this new material. So we know that the speed of light in the vacuum is going to be c. And we know c has value 3 times 10 to the 8. And then we're going to say that the speed of light in the new material is going to be equal to cs. And we've seen that we can write the refractive index of this material as the ratio of c to cs. We can find the ratio between speeds in two different media in terms of the ratio between the refractive indices. So we can see that the distance between the wavefronts is different, so therefore the wavelength and the wave speed have changed. So we're going to say that in material 1, we have a wave speed c1, and then material 1 also has a refractive index n1, and then the second material is material 2, and the light is moving through material 2 with a speed c2, and it also has a refractive index n2. So we can now write the refractive indices in with this ratio between speeds. So we've got n1 is equal to c divided by c1. And we also have n2 is equal to c divided by c2. And we can rearrange each of these equations to make c the subject and equate them. So we've got n1 c1 is equal to c. And then we also have n2 c2 is equal to c. So we can therefore get that n1 c1 is equal to n2 c2, and we can write the ratio c1 divided by c2 as n2 divided by n1. So we've got a ratio between the refractive indices of the two materials and the speeds in the two materials. We know that the ratio between speeds in each media can also be given in terms of the angles of incidence and refraction. So this is material 1 and this is material 2. And we've said that the angle that the light makes with the normal to the interface is the angle of incidence. So that's theta 1. And this angle is theta 2. So it's the angle that the refracted ray makes with the normal. And light is also travelling with a speed c1 through material 1 and c2 through material 2. And we've seen that sine theta 1 divided by sine theta 2 is equal to c1 divided by c2. We equate our two equations for the wave speed ratio to obtain the refractive indices in terms of the angles of incidence and refraction. So we've said sine theta 1 over sine theta 2 is equal to c1 divided by c2. And we've also said c1 divided by c2 is equal to n2 divided by n1. So we can equate sine theta 1 over sine theta 2 to n2 over n1. So we end up with sine theta 1 divided by sine theta 2 is equal to n2 divided by n1. The equation that relates the angles of incidence and refraction with the refractive index of each medium is known as Snell's law. So we rearrange the ratios we've just found to say that n1 sine theta 1 is equal to n2 sine theta 2. And we call this equation Snell's law. So n1 is the refractive index of the first material. So n2 is the refractive index of the second medium. Theta 1 is the angle of incidence. And theta 2 is the angle of refraction. So on a diagram, we've said that the angle that the incident ray makes with the normal is theta 1, the angle of incidence, and this here is the angle of refraction, the angle that the refracted ray makes with the normal. And in this case, this is material 1, and this is material 2, and they have refractive indices n1 and n2 respectively. So now let's look at an example where we can use Snell's law. A ray strikes a surface of oil kept in a beaker on the windowsill at 32 degrees from the interface. The olive oil has a refractive index of 1.47. What is the angle of refraction of the ray? So this olive oil here has a refractive index of 1.47. So our first step here is to draw a diagram and find the angle of incidence, because we haven't actually been told what the angle of incidence is in the question. So in our ray diagram, this medium is air and this medium is olive oil. So we know that originally the first medium is air because the question tells us that the beaker of oil is kept on a windowsill. So now we've got enough information to find what the angle of incidence is. So this is our incident ray, this is our refracted ray. This is the interface between air and the olive oil. And this is our normal to the interface. So we've been told that the angle that the light ray makes with the interface is 32 degrees. So we've been told that this angle here is 32 degrees. However, the angle of incidence is the angle that the incident ray makes with the normal. So we want to find this angle, that's theta 1. So to do this, we're going to do 90 minus 32 degrees. So theta 1 is going to be 90 minus 32, which is 58 degrees. And we know that this is a right angle because we've said that the normal is perpendicular to the interface. So theta 1 is equal to 58 degrees. And also our angle of refraction is this angle here, and that's theta 2. Our next step is to write down the formula for Snell's law and rearrange to find the angle of refraction. So Snell's law tells us that n1 sine theta 1 is equal to n2 sine theta 2. And we want to rearrange this for theta 2 because that's the angle of refraction. So first of all, we're going to divide both sides by n2. So we therefore get that sine theta 2 is equal to n1 sine theta 1 divided by n2. And then we can take the inverse sign of this expression in order to make theta 2 the subject. So we then get theta 2 is equal to sine to the minus 1 of n1 sine theta 1 divided by n2. And now our final step is to substitute in the values from the question to find the answer. So theta 2 is going to equal sine to the minus 1 of n1 sine theta 1 divided by n2. So now we can just substitute in our values. So theta 2 is going to equal sine to the minus 1. So we said our first medium is air. So we're going to approximate the refractive index of air as 1. So we've got 1 multiplied by sine of the angle of incidence. And the angle of incidence is 58 degrees. We've calculated this. And we then need to divide by the refractive index of the second medium, which is 1.47. So theta 2 is going to be equal to sine to the minus 1 of 0.5769, etc. So we need to find the inverse sign of this number here. And that gives us theta 2 is equal to 35.2330. So to three significant figures, theta 2, the angle of refraction is 35.2 degrees.
Hey guys, I hope you enjoyed the video. If you're looking for an amazing A-level physics resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together, let's make A-level physics a walk in the park.